This is great. I get to tell like all the old guys what to do. I love it. This is the last time I'm going to get to do this. Well, maybe not. I might come back right now. Anyway, so tonight we're going to start our meeting off with, as we always do, with our beginner session. Darren's been doing a run of back to basics stuff, and tonight he'll be talking about using your new scope, setup and accessories to enjoy the night sky.
Sweater tonight, so I might have to do a bit different. There we go. This is working. Good evening, everybody. Did everybody have a good Christmas holiday season?
Yes.
Pretty good. I mean, other than the weather being a little overcast and cooler than average and sometimes, and now we're warmer than average. You can't make up the time what it's going to do. Quick show of hands for those of you who are fairly new observers. Did anybody get a new scope for Christmas? Or yeah, cool.
That's why we're here.
Oh, okay. No pressure on me, eh? Anyway, well, that's good to hear. For those of you that are still thinking, trying to decide what you're doing, hopefully this will be some good information for you as well. What we're doing today, basically I'm going to be talking about a couple of different things here. We're going to start with a quick polar alignment made easy. It'll look a little confusing when I start through some of it for those of you that aren't familiar with the technique, but it'll kind of come up hopefully into focus fairly quickly after that. I'll just sort of review for those of you that did get, let's say, a go-to telescope and you have an EQ mount. We'll talk about just some generic procedures that are kind of typical for those, especially if you haven't pulled yours out of the box yet, because with this guy, the way it's been, you haven't really been motivated to take it out yet and try it probably. Also, a two-star alignment method for go-to mounts in general. I'll just talk about that a little bit, just sort of as a primer, because it'll vary depending on the type of mount you have, and obviously certain manufacturers will have slightly different procedures, but the basics will be the same nonetheless. And then we'll also just talk a little bit about eyepiece. Now, this review that I'm talking about here isn't so much a review of different types of eyepieces that you can use in your telescope with respect to field of view. We're going to be talking about expanding your magnification ranges. So if you have, let's say, 2 eyepieces or 3, how you can kind of double it up using Barlow lenses and so on. And a novel way of thinking of magnification. So for some of you, this might be a little new way of looking at it. So that's what we're going to do. I was hoping to also do an introduction on additional accessories and upgrades, but I'm going to pass that on to February because there's just not enough time today with our elections and stuff today. So my apologies as well. Normally I have these laid out a little bit more succinct. I got ill over the New Year's, and I'm fine now. Don't worry, I'm not contagious anymore. But it did kind of lay me out for a few days, so I didn't get a chance to finish this as quickly as I wanted to. All right, so let's get right into it. So for those of you who are familiar with mounts, we have 2 primary ones. We have an all-azimuth mount here. This poor lady's sitting on her knees here. Basically, it goes up and down and side to side. So those of you that use a binocular on a photographic tripod, that's an all-azimuth mount. Okay, so you're basically going up and down and side to side to aim the telescope. Today we're going to be focusing on an equatorial mount. And that's where you would focus. That's where you would have one of your axes aligned to the North Celestial Pole near Polaris. Okay. All right, just a primer for those of you that aren't too familiar, and even those that are, that might be a little rusty. What we have here is, what we have in the case of a German equatorial mount is you have one single axis that's aligned to the celestial pole. So if your telescope was, it would be aiming along this line here, okay, to the observer. And that allows you, when you have it either motor driven or you're manually turning it, you can then track an object as the Earth is rotating, okay? And that's the nice thing with the German equatorial mount, is you don't have to move in both axes. You just have to normally do it in one, okay? There's 2 axes for those of you that aren't familiar with this. The right ascension is the equivalent of longitude on a map, say, or on a globe. We reckon right ascension with the, what we call it, this would be the equivalent of our prime meridian, and what we use in this case is called the vernal equinox. That's the position that the sun is just as it's crossing the equator going into spring. Okay, that's your Greenwich line, if you will, for the celestial sphere. And then in the case of a declination, what we do is that's the equivalent of our latitude. So if you project on our globe out to the heavens, our equator, that's our celestial equator, and then you're doing degrees north and south from that, or in this case, plus or minus. Plus being above into the northern hemisphere, and minus to the south. Another just reminder for everybody as well, why we see a changing of seasons and constellations. I talked about this a couple of months ago when we were talking about doing dead reckoning of stars or star hopping. But this is just another diagram just to remind you that because our Earth's rotation is in the same direction that we revolve around the sun, what this means is we reckon our time in solar time, which means that we always look at the same time that local noon would be. So it actually takes an extra 4 minutes for that to happen. When we're looking out at celestial objects, we actually project that out, and because they're not moving relatively, or they're moving relatively slowly for all intents and purposes, they're fixed compared to the rotation of the Earth in the time of day. What it means is that we actually have 4 minutes less per day to have an object be in the same direction that we're pointing to the same time. So what this really translates to is that something rises 4 minutes earlier every single day, and over the course of the year it'll be back to where it was before. That'll be relevant a little later when we're talking about polar aligning, of course, in general as well, for when you're just considering looking at objects. Okay, so we're going to get into polar alignment made easy with all that confusing stuff that I talked about already. So here's an example with this little GIF here. I thought it was kind of cool, so I thought I'd add it in. This kind of gives you an idea of what you're doing when you're using a German equatorial where it's motorized. It's going to track with the Earth's rotation. That's the idea. And so the primary axis here is aiming along our polar axis towards the North Celestial Pole. We're very lucky in the Northern Hemisphere because we actually have a relatively bright star close to our pole, so it makes it very easy to do polar alignment. If you're in the Southern Hemisphere, it's a lot more complicated. I'm not going to talk about Southern Hemisphere today, just wait. So here's an example of our North Celestial Pole here, and as you can see, Polaris is fairly close here. I've just left all the other star labels and other stuff just for clarity. Now, in this particular time of year, you'll notice that I'm going to be talking a lot about clock position. This is a modified technique when we're talking about doing polar aligning with your eyepiece rather than with, let's say, a polar alignment scope. For those of you that don't have a polar scope, this is a method that you can use your eyepiece and telescope to align to the celestial sphere, or to the North Celestial Pole. So basically what you do is I'll go through these very quickly, but you level and square them out. When I say squaring, what you're doing is you're putting your telescope top dead center. So what will end up happening is your counterweight axis will be perpendicular to the ground. Okay, and that's squaring up the mount. You'll pre-align it to north. Obviously, you want to be aimed in general towards north, or otherwise there's no sense trying to do this at all. Then you want to confirm and adjust your latitude scale for location. We're here at about 50 degrees north in Winnipeg. So if you left it at 50, you're just going to tweak it a little bit, but you're pretty much bang on. If you were going to travel with your scope, say, down to somewhere in the States, like Colorado or something, you might want to be around 42, 43, or maybe a little lower, depending where in Colorado you're going. And then you want to use your finder or RDF, if you have a red dot finder or reticle or something like that, to be able to find Polaris first, and then you'll place it in the eyepiece. Then the idea is as I say, we determine the clock position of Polaris, and there'll be some caveats here depending on the type of telescope you're using, so I'll talk about that. We move the Polaris to the position relative, so that, like as an example here with our eyepiece, and I have better diagrams to show this later, you would move Polaris out towards the edge of the field, the relative clock position, and then therefore your North Celestial Pole is now in the middle of the field of view of your eyepiece, and then you're ready to go. So we'll kind of go through this. It's not too complicated, but I just want to make sure I do it in enough detail for those of you that aren't familiar with the technique. Once you've done it once or twice, it's a piece of cake. You can be up and running in 2 to 3 minutes or less. So again, we level and square them out, and then pre-align to north. A lot of people will, especially if you're going to be viewing and the weather's pretty good, you might want to pre-align with the compass in the daytime or in early dusk before the stars are out. That way you're all set to go. The telescope's already started to cool. And then when it starts to get dark, you just fine-tune it, and away you go. This is the latitude scale, and again, like I say here, in Winnipeg, we're about 50 degrees north here. We're just slightly less than that, it's like 49.96, depends on where in the city you are, but 50 will get you in the ballpark anyway to get started. Way to find Polaris, very easy. We have two different ways to do it. One way is to use the pointer source here in the Big Dipper, and at various times of the year, the Big Dipper will be, towards the north, kind of near above the pole star, and at other times it will be down low. If you find it's down low like this, or maybe you might have some trees or neighbor's house or wherever you're doing, and there's something obscuring the pointers and you're having trouble finding Polaris, you can also use the W of Cassiopeia here, and I use the right-hand side of the W, just sort of almost split the difference between that little second W, and that gets you right to Polaris as well. It's fairly easy to find. Now, just a little bit on Polaris. This is the location. This is the location of the celestial sphere. It's almost bang on the celestial pole. It'll actually get closer as we get towards 2100, and then it'll start to drift further away. But for all intents and purposes, we're going to be well within a 2/3 of a degree for the next foreseeable future here. And just coincidentally, for those of you that do want to try this technique, if you don't have a polar alignment read, if you want to see how good the technique can work out, turns out this month, in a couple of days, at 8 p.m., Polaris will actually be right above the North Celestial Pole, so it would make it a good opportunity to try this technique, because you don't have to worry about it being on either side of the meridian. It will be right at the meridian there, so it'll make it really easy to do this as a primer. Now, bear in mind, if you do it days later, you'll have to take into account that 4 minutes per day, right? So if you were doing it, let's say 2 or 3 days later, you're going to have to be 8 or 12 minutes earlier than 8 p.m. to have it bang on. Okay. So with a manual German equatorial mount, one that isn't motorized, you'll have these slow motion control knobs are used typically in lieu of the motors that you'd normally have, okay? And so if you're using a manual mount, what you're going to do is, once you've done this polar alignment and you're looking at an object, you're going to continually turn the knob periodically to keep the object in the field of view, right? Because it's obviously going to drift out of the field of view if it's not motorized. So that's just something to be mindful of. A lot of these will also, whoops, I'm going to go back here for a second. A lot of these will have polar scopes, or you can get a polar scope optionally. And the nice thing is here you can, there's varying ways to do it, but usually you'll set the reticle in here. I've got another picture on the next slide that'll show this, but you can actually sight along here and do your alignment that way in lieu of doing this eyepiece technique that I'm talking about. But if you don't have one of these right away, you can use the eyepiece technique. Okay, next slide here. So this is what these polar scope reticles, this is just some typical examples. Many of them will also have, again, sorry guys. Many of them will also have a secondary star, like Delta Ursa Minoris, as a second reference, and that helps you have 2 stars to be able to align to. So the idea here basically is you'll rotate this until Polaris this will have index marks for the time of year in the month of the year. And so what you'll do is you'll rotate it until you're there, and then what you'll do is then you'll adjust your latitude and your azimuth. That basically ends up being your altitude and azimuth to align the pole properly, and that'll center then Polaris in the little circle here. Oops, I did it again. Sorry, guys. So this little circle here is where Polaris is going to be, and then your North Celestial Pole, of course, will be aligned bang on. So that'll give you that. Now, when you're doing it with an eyepiece, there's something else to consider here. When we have a terrestrial view like this, or through binoculars, the erect image view, this is the orientation that we would see in the eyepiece, or eyepiece of an optic that's giving you a non-inverted view of some form. The inverted image here on the second middle portion here would be through a reflector, a refractor, or SCT without a star diagonal. So the reflector would be just through the eyepiece and the focuser. It's basically flipped twice. So that's the equivalent of a rotation of 180 degrees. You'll notice that the north is now at the bottom, south at top, and west and east are reversed. So if I took this and flipped it exactly upside down, 180 degrees, that's what you're seeing. So even if you were to look at the moon, say, naked eye, and then let's say it's 50% illuminated, and then you're looking at an eyepiece in a Newtonian, it'll be right upside down, it'll look upside down and backwards. In the case of a telescope like a refractor, an SET with a star diagonal in it, what it does is it's erect vertically, but it's horizontally reflected, so you'll have it backwards, left to right. And this is very important because when you're determining that clock position for Polaris, either from an app or whatever, and you see that it's say, at the 2 o'clock position, in an SET, I'm going to do a mirror image and I'm going to be at 10 o'clock now. That's where I'm going to want Polaris to be in the eyepiece, okay? So this is very important to remind yourself of this, otherwise you'll be way off on your polar alignment. So I just thought I'd throw in some clocks just to give the idea of the concept here. Maybe that's a little clearer than the galaxy picture that we had before. All right, so with a simplified view of Polaris near the North Celestial Pole here, this should be actually true field of view. I apologize, that's a typo up here. This should be TFOV. So this is a 1 degree circle. So if you had an eyepiece that gave you a 1 degree field of view, this is where Polaris would be relative to the field of view. So you're going to have it just slightly out of the edge here. If it was a 2 degree field of view, then it would be just almost, well, 2/3 of the way through, almost 3/4 of the field edge in the appropriate clock position. Now, with a refractor SET view, again, like I say, you would end up flipping it vertically. So in this case, instead of being at 7 o'clock, you would be now at 5 o'clock. So you would be orienting Polaris initially would be centered, then you move it to the 5 o'clock position, the appropriate distance, depending on your eyepiece. I'll talk more about that in a minute. And then in the case of a Newtonian, you're going to go obviously 180 degrees over to have it positioned correctly. Now on a motorized gem mount, some will have polar scopes as well. Often in some cases, you don't need a polar alignment scope because they'll have an auto function. So just a quick review of these for those of you that have, let's say, a go-to. There's different ways of doing it, but basically the idea here is you want to square or level the mount and align it as described before, just to make sure it's already preliminarily set to north. Then you're going to, a lot of them will have index marks where they're slightly offset from that. And that's to allow the firmware and the motor control software not to get into a redundancy. And so when you go to power it on and actually select polar align, it'll slew just slightly, and this is where it'll think Polaris is. So now you'll just move your mount to center Polaris in the eyepiece in this case, okay? And then you just, once you've adjusted your mount to show Polaris in the eyepiece, you just say, okay, it's aligned, and then it'll go to some sort of a 1, 2, or 3 star alignment, depending on how the particular mount is set up. And you're ready to observe, okay? So then in that case, you don't need to do all this eyepiece alignment or even the polar scope alignment, although that's a good way to get started quickly. Now, for those of you that have an Alt-Az go-to mount, it's a little different. Again, there are some variants to this, but this is pretty basic. Again, you'll level them out. Some of these Alt-Az go-to systems, like an Optron, some will want them the scope vertically up and oriented so that the mount is sort of roughly aiming south. Some will have it level north. Some of the Meade ones are level north, as an example. So, you'll have to use your manufacturer's instruction manual depending on how you want. That's the default way of setting up the scope to sort of index the scope before you power it on. And then once you've done that, when you power it up, a lot of these new mounts will have GPS already on them. So if they don't, you'll have to set the date and time manually in the time zone and so on. And then from there, you'll just go to your 2-star alignment and slew to your stars. Now there's some things to be mindful of. We'll talk a little bit more about this in a couple of slides, but the idea here is you want your alignment stars, whether you're doing this with a German equatorial or an Alt-Az, you want them to be far enough in altitude between the 2 stars and azimuth so that you get a good sky sampling. That way you have less error when you're slewing. There's no sense having 2 stars, say, 30 degrees apart, because that just gives you a limited sample of the sky. It doesn't give you as much pointing accuracy. And then, of course, once you've done that, you're ready to observe. Now, this is an example of some of the brighter stars that are typically used to align most mounts, whether they're Alt-Az or German equatorial. For those of you that attended a couple of months ago when I was talking about star hopping, I mentioned about really getting to know some of the bright stars really well, because that'll help you find them very easily without having to look on a map. Well, these are some of the stars that you can consider. And there'll be some that you'll find as favorites, depending on how you're observing and what times of year you like to observe. You can pick a handful of combinations. and from there those can be used as your stars. One example here would be Duvet and Spica. At certain times of the year, Duvet will be almost straight up and down, almost vertically up, and Spica will be just starting to rise, so that'll give you a good sampling in altitude, as an example. You can also use planets too. So if, let's say you have a bright star like Vega in the early summer or late spring, it's usually one of the first stars to pop out of the sky. You could use Vega and maybe Jupiter if you wanted to do your alignment initially, and you can always realign later if you're finding you're slowing not accurate. So never forget to do that. I tend to avoid using the moon because it's just a little tougher to estimate that it's in the middle of the field of view, right? Whereas these smaller objects are much easier to center. So just some final thoughts on this before we get on to the rest of this here is just remember to level square and aim north with the mount. Use your finder or RDF to find Polaris. That's the easy way to get started. If your finder or RDF isn't aligned to your eyepiece, you'll have to obviously fine tune it before you do this on a routine basis. It makes sense to have your finder or red dot finder or reticle aligned to your eyepiece because obviously it doesn't function as a finder otherwise. You're just guessing, right? For go-to slewing, another thing just to be mindful of here is make sure to slew in the direction of approach to minimize backlash. All of the motorized mounts will have slight meshing incongruencies in the gears unless they're belt-driven ones. And so the idea here is you want to minimize going too far over, and then when you go back, you've left a little bit of space in the gears because then it'll erroneously think that it's positioned here, but it's actually positioned here, and you'll start to get slew errors eventually. Use the widest field of view available for your eyepiece choice if you're going to do this eyepiece alignment method. And like I said, aim Polaris to your appropriate clock position using the telescope's image that you have depending on the telescope you're using in the eyepiece. Now just some comments about different eyepieces. I'm not going to get into this in too much detail, but the idea here is you want an ideal eyepiece for doing this polar alignment technique has about a 1.3 to 1.4 degrees. That way you would put Polaris right on the edge of the field of view and at the appropriate position given the field of view in your eyepiece and the orientation that you've compensated for. Your north celestial pole will be very close to bang on. You'll be within usually a tenth of a degree if you do it properly. One way to do this more easily is to use something like a reticle eyepiece. This Orion one's really nice because it has a large field of view. And the nice thing is this can also be used when you're doing star alignment with a go-to scope as well, because now the crosshair, you can just center your object right on the crosshair and boom, there's no guesswork. So it's a very handy accessory to have. So these are not cheap. They run usually in the $90 to $150 range, but they do come in very handy for a wide range of applications. So I do recommend down the road at some point, if you don't have one, it'd be a good idea to look at getting one like this. Here's just some quick examples here when we're talking about polar alignment with different types of common starter scopes or even just common telescope configurations in general. Where we have the red showing, obviously Polaris cannot squeeze into the field of view in order to be properly polar aligned, so you'll have to have it out of the field of view slightly. The easiest way to do that is if you're orienting Polaris to the edge of the field of view, make a note of how many turns on your axis that you're doing. And once you know the field of view of your eyepiece, you can just say, okay, I need to be an extra third of a degree, that's 4 turns up and 3 turns to the side, and then you're good. Once you kind of get used to that, it's very easy to do that moving forward. The other 3, of course, you'll have Polaris fitting in the field of view, and in fact, in the bottom 2, the left lower and left center, or center lower, you'll actually have Polaris right at the edge of the field of view for this, for these particular choices. I decided to, because a lot of the entry-level scopes usually only have 1.25" focusers, not all of them, but many of them do. I decided to stick with the 1.25" format for this example. There are scopes that have 2" focusers and 2" accessories, and that does lend to a lot of other combinations. I'll be talking about that next week in some more detail. So we'll just talk about eyepieces in general a little bit. And just a refresher for those of you that maybe attended the talk that Brendan gave a couple of months back on eyepieces and telescope optics in general. This is just sort of a refresher for some of you. Obviously, the more esoteric eyepieces with larger fields of view, they start to have more elements in them. This is by no means fully comprehensive. There's some new ultra-wide, or you could almost call them extremely wide eyepieces now in the 100-degree range. They give you huge swaths of sky. They're not cheap either. They're very expensive, a lot of them. The good ones are anyway. But this top row here, these are typically the earliest eyepieces used in telescopes. And they typically have very narrow fields of view, so you tend to be thinking like you're looking through a tunnel. Okay. The workhorses are the Plossels, typically, or the orthos. And the Plossels often will come with most of the starter packages. You'll usually get 1 to 2 eyepieces coupled with a telescope. And those are usually Plossels. They have typically 50 to 52 degree field of view. It's quite common there. The orthoscopic are excellent planetary eyepieces, and they're just a little narrower than a Plossel. Then of course we can get into wide and super wide, ultra wide. It depends on where you want to draw the divisions. Barlow lens here will have, in this case, this is an accessory I'll talk about in a few moments. The Barlow will actually effectively change the focal ratio of your telescope to give you some extra functionality when you're using different eyepieces. So just a refresher for those of you who maybe saw this before with Brendan, it's just a different diagram, but 2 important parameters to remember or formulae. One is the focal ratio of the telescope. This will come in very important in a few minutes here for us. It's the focal length of the telescope. In this case, it's 900 millimeters divided by the aperture, which is 102. This one's an f8.8. So if you ever see an f ratio, like an f9, f7, f8.8, f5.4, that's what that number is calculated from. So it's the ratio of the focal length of your optical instrument divided by the diameter of the aperture. And then the magnification, depending on the eyepiece you're using, it's the ratio of focal lengths of the telescope over the eyepiece. In this case, this one's 36 power. So that's the basically that same formula for magnification there. When you were calculating our true field of view, you remember I was talking before about different fields of view, and you saw the little table I had here. Basically what we do is we take the apparent field of view of our eyepiece divided by the magnification. That gives us our true field of view. So as an example, if I had a telescope, the eyepiece that was giving me 100 power, and I was using, and it was a Plossel, and let's say it was approximately 50 degrees apparent field of view, then you'd have half a degree. 50 over 100 is a half. So that would give you a half a degree true field of view. You could just, the moon would just be outside the full field of view of the eyepiece. Okay. Exit pupil is another important parameter that we use. We talked about this when I did my talk on binoculars, and this is going to kind of do a segue into thinking of a different way to calculate magnifications instead of using focal length ratios. But the exit pupil, just to remind everybody, is the diameter of the light cone coming out of the optic, your ocular lens, and then you're actually, when you're looking through, it's the one that's providing the diameter of the light cone there that you're looking for your pupil. Okay, and we can calculate it a couple of different ways. One way is objective diameter divided by magnification. So if I had, let's say, a 100 millimeter telescope and I was at 50 power, I would have a 2 millimeter exit pupil. Okay. The focal ratio, again, is the focal length of the scope divided by objective diameter. And another way to calculate the exit pupil, this is just kind of a novel way, is to use the focal length of the eyepiece divided by the f ratio. And that's what we're going to talk about in a few minutes here, because these two are interrelated. They're inversely proportionate to each other. And this is a very handy way of calculating your magnifications or figuring out a good range of magnifications for eyepieces. Well, this sounds really confusing. I know. Okay, Mom, what kind of eyepieces can I use in my scope? Cut out with all these formulas. All right. Well, let's just kind of determine here. So this is what I'm talking about here. I like to think of MED or MED as kind of a nice little mnemonic to think about this. So basically, the magnification times the exit pupil gives us our objective diameter. Okay? So if you remember that, then you can rearrange this formula to get your exit pupil very easily, depending on what kind of magnification you want. I find the best low power range is typically, on average, around 4. You can go as far as 7 with an eyepiece, but one of the problems we'll have is the same thing with binoculars. You end up with the light cone, depending on how your dark adapted pupil dilates, you may not necessarily have it wide enough to accommodate the full light cone, and then you'll start to actually vignette the amount of light coming into the instrument effectively. So it's almost like stopping down your instrument. So I tend to avoid that by staying less than 5.5, especially as you become an older observer. The other thing too is that as we use more and more towards the center of our pupil, we actually get much better resolution. And we start to get more significant aberrations as we're viewing on the outside edges of our pupil. So you try to avoid this by going a little smaller there, okay? Medium powers typically are in this range here. What I mean by optimal power here is that once we start getting into around the 2.5 millimeter range or so for the exit pupil, you're starting to get into the regime where now you're using the sharpest part of your lens, and now you're kind of crossing over to where you're starting to get the maximum amount of detail from the telescope coming in. I'm going to move for 10 here. Yeah, pretty close there, okay. And then when we get into high power, usually 1 millimeter is a good starter point, and then very high power, of course, maybe 3/4 is a good one, and then of course your maximum power here, really the sky's the limit, but the problem is that because these are diffractive optics, we reach a point of diminishing returns where the object, when we start magnifying it any more than beyond a certain point, it's just empty magnification, there's nothing there, right? You're just, if anybody of you have done this with pixels on a digital image, as you start to blow it up, you reach a point where I can keep blowing it up, but there's no benefit, it just gets blurrier. Same kind of thing in a telescope, for those of you that haven't done this before. Okay? So this is kind of a novel way of thinking about it. I've got an example here I'll talk about in a minute here. I'm almost done here. So one of the reasons we are doing this approach is see if a lot of people will try to get the whole eyepiece set in order to get a range of magnifications for their scope. But do you have to do that? No, because you can actually use a Barlow lens, which is a really handy accessory, also known as a telenegative lens, to be able to do the expansion for you, and it allows you, with very minimal number of accessories, to be able to expand your magnification and eyepiece set without having to buy every single eyepiece under the sun. So basically what's happening here is if this was our normal light cone, what the Barlow lens does is effectively shallows it out here. So it slightly changes it. So effectively what we've done is we've changed the focal ratio of our telescope. So if you have a 2x Barlow lens, it's like doubling the focal length of your scope effectively. And so, or you could think of it as having the eyepiece focal length, I guess, in a way. So if I had, let's say, a 20 millimeter eyepiece in here and I put it in a 2x Barlow lens, that combination is like putting in a 10 millimeter eyepiece. Okay, that's kind of what we're talking about here. So this gives us 2 different magnifications with one eyepiece. So here's some examples here. This is just a very simple one. A 8-inch dog here. In this case, let's say I had one that came with a 10 millimeter and a 25 millimeter colossal eyepiece. Let's say I bought, or it came with a 2x Barlow. This is an example of what you can get for magnifications and exit pupils. So you can see as we go to higher magnifications, the exit pupil goes down because they're inversely proportionate to each other. So this just kind of gives you an idea of what you can get as far as power ranges. Now you'll notice here we have a bit of a gap between our medium and high power for this particular type of instrument. We have a little bit of a gap here too. We kind of like something to kind of round this out. So now let's say I get another eyepiece, 15 millimeter. Now look what we've got. We've got a beautiful range of different magnification. 48, 80, 96, 120, 160, and 240. It's a really nice smattering of ranges, but I didn't need to buy 6 eyepieces. I have 3 in a Barlow. So if you select the eyepieces, and you'll have to do this depending on the type of telescope you have. If you choose your eyepiece ranges so that they work in, so you don't have redundancy. Like if I had, let's say, a 20 millimeter Colossal, if I doubled it, I'd have a 10, so there'd be an overlap there. You try to select that combination so you don't get an overlap as best as possible. Okay, so there's an example where now I have 3 I had 2 in my kit, so now I bought 1 eyepiece and a Barlow, and I've got 6 magnification ranges. That's kind of what I'm trying to pass on to you folks here today. Another little point about magnification, I know a lot of people have a tendency to want to, when they get a new telescope, I want to see as close as I can. So what do? They ramp up the magnification up to 250 power or whatever they have in a combination. That may or may not allow, the scene may or may not allow that. So try to avoid that. I'll be talking more about this next week when we talk about observing techniques and so on. But the idea here is use just enough magnification to see the object clearly. Because you're better to do a little bit lower and have a nice steady image rather than try to blow it up a little bit. And now the seeing is kind of falling apart. And now you're seeing it undulating in the sky all the time. it's very difficult and frustrating for people to enjoy the view. So in the next beginner session, that's pretty much it for tonight here. I'll be talking about enhancing and expanding your telescope, and we'll talk about expanding the field of view available in 2-inch format eyepieces. We'll talk a little bit more about the apparent field of view and how that impacts us when we're looking through different eyepiece formats. We'll talk about retrofitting and upgrades to mounts and focusers a little bit, kind of an intro on that. What you'll need to shoot through your scope with a camera, an introduction of T-rings and other accessories that you can maybe meet your DSLR to. And then finally, this will be kind of useful. This is sort of touching on what I just talked about. We'll talk about different observing techniques for planets and DSOs to kind of get the most functionality out of your instrument. So that's basically it tonight. Thank you very much, everybody. Any questions? Okay. Anybody got one or two? I know that was a little rifled through. I must have totally confused everybody else. Good work.
Hey, just a comment to make. Most people with a computerized telescope, it's enough to put a level on it, the level at the point in north, and say go.
Yeah.
As long as it knows where it is and what time it is, it'll get you close enough. Secondly, if you've got a small thing like a tracker, stick a laser on a flat part of it, have somebody look at the pole with a pair of binoculars and adjust the laser position using your azimuth and altitude screws, not your slow motion control, until it's pointed approximately where it should be.
Yep.
It'll be close enough to do all the tracking you want. All this other stuff is refinements for photography or really precise. It's pretty simple to get going.
No, of course. You're right. Thanks.
Oh, hello. My name is Brendan, and this is the January meeting of the Winnipeg Royal Astronomical Society of Canada. If you're here for exam, you're a month late. And, I'm going to take that last one. That's a joke. Anyway, is there anyone new here? Hey, welcome. You picked a great month because we're doing elections this month. Super exciting astronomical event. It's just a thing we have to do every year just to keep the thing running. But our agenda for tonight, well, we just enjoyed Darren's talk on accessorizing and using the telescope. He did misspeak a little bit in that it won't be next week, it'll be next month that he continues to go. If Darren wants to come here next week and give the presentation, I mean, by all means. Just I wouldn't expect him to be here. I'm currently running through the announcements. Ryan will be giving you a tour of what's currently up in the night sky. I will be giving you a rundown of what's new in the science of astronomy. And like I said, we have elections. Then we'll be taking a break for refreshments. And then our guest speaker from the U of M is Michelle Boyce, and she'll be talking about the dark universe. Looking forward to that. Anyway, announcements. Public. So every year we do a public in January because there's no way we could ever manage to wrangle everyone for December. So we just push it off a month and keep it festive for a little longer. These are the details. I will send this out via email to everyone that's in the club. So feel free to come on down. Moving on, we have a new YouTube channel. For the longest time, we've been using Abdul's personal channel to host our videos. And I had just been putting this off for far too long and finally took care of it. A couple things to note. So Abdul went through the laborious effort of uploading all the videos that we have, which is great, and they're all in order, which I love, thank you. YouTube is terrible for letting you actually display this in a way that makes sense, so if you don't upload them in order, it will then be uploaded, it will display in the incorrect order, and you can't change that. Anyway, a couple things to point out. One, this number of 10 subscribers, if we get this up to 100, then we can actually have a YouTube /channel /RASC Win or something like that. So if you could, please subscribe. I've created this temporary link just because it would be easier for it to write down. So it's bit.ly/RASCWin. If you go there and subscribe and get that number up to 100, then we can make an easy to link and easy to find channel. I will send this out. I will definitely send out a link. We'll be getting the new. What I'm saying right now is being recorded and will go up on YouTube. And when that video comes out, I will send it out and also send out a link to the channel. What is Centrix? Did Mike make it up tonight? I don't think Mike's here. Okay, I don't see Mike. So for the past few years, Mike Caracas has been our Centrix editor. Has been doing a phenomenal job with it. He took on some more responsibilities with it, and he expanded it quite a bit beyond its original mandate. He's done a phenomenal job with it, but now life has gotten busy a little bit for him, and he has decided to take a break. So I did want to say thank you to him. He's not here tonight, but he's done a phenomenal job, and that's definitely worth recognizing. But that said, if it's something that you might be interested in, we are looking for a new editor. Now, this is a position that has to be appointed by council. Jay will likely talk a little bit about that come election time, but just so you know. The open houses are starting back up again at the U of M. The next one will be on January 30th. The next topic is From Fuzzy Clouds to Island Universes, the history of extragalactic astronomy. Sounds actually pretty cool. I'm a little disappointed we couldn't get that in here tonight, but I'm looking forward to the Dark Universe too. That was actually another one of the U of M ones, so we might actually get this talk at some point, but you never know. So I would recommend, go check this out. OCAMIC. These are the events that we do, well, we help out with at OCAMIC Marsh. They do this astronomy night on the, I think it's the third Thursday of every month. The next one's on January 17th. This one actually features a pretty special guest speaker. It's Ralph. He'll be talking about meteorite hunting and collecting. So feel free to head on out. If you do bring a telescope, they will waive the fee for you. So telescope loans. If you're a club member, we have telescopes that you can borrow. The collection of them consists of 2 dogs and a solar scope with a nice little tracking mount on it that you can also use for photography, FYI. You can slap a DSLR on there pretty easily. Stan, what's our status?
I have 1 Dob available.
Okay, there is a Dobsonian available. I don't know if it's the white one or the black one, but they're all the same. But I do really recommend this if you're looking to get into the hobby and you don't have a telescope. These are great options for you. Again, members only, but you get to take it out for a month at a time, and it's just a good way to get involved and get into it. Glenley Observatory. If you would like access to our club observatory, you need to be a member. But all you have to do is get some money to Brian, and he will get you a key and walk you through how to use everything that's on site there. It's a nice place. It's just south of the city a little bit, so you have a little bit of the sky glow to the north. Stan?
You might want to update that chart and include that 1 Dobsonian that's inside the warm room now.
Oh, that's right. That's a good point. Yes. There is an additional. How big is it?
6?
6 inches.
There's a 6-inch Dob as well on top of that. So there's a nice little scope out there that you can also use if you don't want to haul around it. Try to use it over the 14. So it's and it's actually also got there's some nice eyepieces and filters out there, and so there's a good collection of equipment out there for you to use. Members Observing Night, Brian, you said tomorrow night?
Tomorrow night, yes.
Okay.
Looks promising.
Yeah, we'll try for tomorrow night to see how it goes. So feel free to show. What time?
What's your question?
Say like 7 o'clock.
Yes.
Let's make it 8.
Sure, let's make it 8. 8 o'clock. If you'd like to show up for a members observing night, we'll try for it tomorrow. We'll see how the weather shakes out. And explore the universe. So Dennis Lyons has been our local champion of this program. This is a really great way to get yourself into astronomy. The program basically consists of a bunch of objects that you can go out and find, and it's geared toward beginners. It's a really great way to get into it. Dennis also asked if I could show this video. So this is something that has been put together by, I think it's the Halifax Center? Yeah. And they're really good videos. They actually have a second one, but I'm just going to show the first one. If you want a nice, easy link to go and find it, I'll send this out via email as well, but I created this just for the heck of it. So bit.ly/RASC-ETU. And that'll take you to this video, and you can find the other videos there. Get that. While I'm loading this up, are there any other, anything else from council? Any other announcements I missed?
Hi, I'm John Reed, amateur astronomer and author of the 50 Things to See in the Telescope book series. I'm also a member of the Royal Astronomical Society of Canada, a charitable organization with over 5,000 members across Canada. The RASC, or RASC, does a lot of public outreach on astronomy. But we also have fun observing the night sky with our eyes, binoculars, and telescopes of all sizes. This is one of 3 videos exploring the many observing programs the RASC has to offer. In this video, we'll look at 2 beginner-level programs, Explore the Universe and Explore the Moon. So why follow observing programs and earn certificates? Having a goal focuses your attention and enriches your observing experience, and it provides a sense of accomplishment. When you complete a program, the RASC will issue you a certificate. Some certificates come with a colorful lapel pin. Details on all the programs can be found online. See the video description for more details. Now let me tell you about the beginner-level programs. For these, you only need your eyes, binoculars, or a small telescope. You do not need a special observing location with dark skies. Your backyard is fine, even if you live in the city. Let's now discuss the Explore the Universe program. Explore the Universe offers a certificate and pin. It is a beginner-level program, open to all. You don't even need to be a RASC member. Most objects require just the unaided eye or binoculars, but some objects may require a small telescope. Here's how to get started. You'll need to download 3 things from the RASC website: a list of objects, observing report forms, and an application form. For additional help, an Explore the Universe guidebook is available to purchase from the RASC store. The program explores 110 objects divided into 5 categories: constellations and bright stars, the moon, the solar system, deep sky objects, and double stars. Only half the objects in each category need to be observed. The choice is up to you. When you're finished, present your logbook to your local RASC center for validation, and they will issue you your certificate and pin. Now we'll talk about the Explore the Moon program. Explore the Moon offers certificates for 2 versions, one for binoculars and the other for small telescopes. Explore the Moon is a beginner-level program based on the information found in the RASC Observer's Handbook. After completion, you'll be prepared for more advanced lunar observing, such as the Isabel Williamson Lunar Observing Program. Explore the Moon is great for learning how to use your binoculars or telescope for astronomy. It is suitable for the urban observer with no worries about light pollution. This program can be completed from your backyard. The binocular program includes 11 lunar seas, 26 prominent craters, and 3 mountain ranges, for a total of 40 objects marked on a single map. The telescope program includes 16 lunar seas, 68 craters, 16 mountain ranges and valleys. There is a total of 100 objects marked on included charts. Also included are mirror reverse charts for telescopes that flip the view from left to right. When you're finished, present your logbook to your local RASC center for validation, and they will issue you your certificate and PIN. So that's it for the beginner level observing programs. Be sure to watch the other 2 videos in this series, where I tell you about the intermediate level and advanced level observing programs that the RASC offers. Don't forget, the stars belong to everyone.
Yeah, I thought that was a good summary video, and probably better than what I tend to go on about every month. And the other videos are quite nice too. For the Jets fans, FYI, they're up 2-0 after the first. Hey, Brian. Brian didn't have his presentation. So what we're going to do is, this is going to go fetch it on his laptop. While he's doing that, no. So, okay. So I will be, I'll be giving you a rundown of what's new in the science of astronomy. Ian Cameron liked to do this thing where he would give you some hint about what the topic was. This one's pretty obvious. Like, this is way less esoteric than what he used to do. Anybody? Chime. Okay, so the Chime telescope. Not bad, right? Not bad. So this, despite appearances, is a telescope. It's a radio telescope, and so it's a Canadian effort located in British Columbia, and it's searching for one of its. I mean, it's searching for a lot of things, but one of its looking in the radio spectrum, right? And so what it's looking for, one of the things it's looking for are fast radio bursts. And I'll talk a little bit. So what are they? They're high energy astronomical phenomena, and from what we know, of unknown origin. We don't know where they're from, and they basically last a few milliseconds and then they're gone. They're visible in radio, and that's it. This was put together to try and observe more of these, and it came online in September 2017. Now I work in computers for a living, So I went and dug up. A scientific paper on this instrument, and of course, rather than look into the science of fast radio bursts, I pulled up the schematic that showed me all the cool techno stuff. So I'll go through this quick, but it's just, the point here is basically they pull in an incredible amount of data and do a ton of processing on it. So what we have here are basically these inputs that go through these machines. There's 6.5 terabytes a second coming through here, actually terabits a second. Okay, it's an incredible amount of data. It gets processed by this, and there's a lot of details I'm going to get wrong about this. There's a ton going on here, but basically a lot of processing. At a certain point, I think when you get to this thing called the X engine, which sounds super cool and intimidating. You actually get down to, I think, like 60-something gigabits a second. So they've done some processing on it at that point. And then when you get to the chime device, at that point, it's reduced quite a bit more. So each of these guys has 256 processing nodes and 64 gigs of RAM. There are 45 10-terabyte hard drives for on-site storage. There's an incredible amount of data that's being pulled down by this telescope. And it is, and so it's interesting, like the time that it takes to process all of this, there's a lot of heavy computation that's going on as well. So they're pulling in an incredible amount of data, but then to process that data is another significant challenge. Now, getting back to fast radio bursts, I like this quote. We have more ideas of what they could be than we have actual detected fast radio bursts. We've detected 36 of them. That's it. Their initial discovery was in 2007, 13 of which were actually discovered by Chime, and that actually happened during the pre-commissioning phase. Now, again, during that pre-commissioning phase, they were collecting all that data, but then it took them a lot of analysis to actually go back and look and confirm that that's what they were seeing.
Actually, the first one detected was around the last week of August. This was my last week on that project.
Oh, right on. I didn't know you worked on this. Shoot, I should have reached out to you. I'm getting so much wrong, aren't I?
No, I'm pretty good.
Okay.
I don't have those fingers in my head anyway.
Oh, that's good. That helps. Now, the interesting thing that Chime discovered, this is why it became relevant in the news media recently. So, of the ones that have been discovered, they've only discovered one that is actually repeating. So effectively, all those ones that I talked about, all of those ones, like the 30-something ones I was talking about, they've looked on, and that was it. Well, they looked on and looked off, in very, 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 very fast, and that was it. Right? And we've actually, so this is the one that was discovered back in 2015 to be repeating, and Chime discovered another repeating FRB. So, pretty cool. And it's the Chime telescope is still fairly new, so I anticipate that they're going to be finding a lot more as they continue to move on. So, bringing it back.
Could I add just one quick?
Yeah, absolutely.
The Chime telescope has about 1,024 beams pointed up at the sky. So it's an all-sky view.
Yes.
And its bandwidth range is 400 megahertz from 400 to 800 megahertz. And basically, because it has a whole sky view, it has a better chance of seeing it, and it's in a radio frequency range that hasn't been observed by others, but predictors more sources.
Right. Yeah. And so it is looking at a lot of the sky a lot of the time. At once. And that is actually, I assume, what translates to all the data that is coming into that thing, which is tremendous.
Yeah, it's humongous.
Yeah, it's crazy. So, life around a red dwarf. Really unlikely. There was the Hubble Space Telescope and European Space Organization. Space Organization. I forget. The ESO. They were looking at a red dwarf star and looking at its protoplanetary disk. Now, red dwarfs have a lot of other problems. They can be quite violent in terms of spewing a lot of radiation off. But actually, as it turns out, they have a bit of an issue with maintaining their protoplanetary disks for an extended period of time. So this was an image taken in 2011 and 2017, and this is this blob. So this is the star. They've blocked it out here. The name of the star is AUMIC, and I presume that the southern hemisphere constellation. But the important thing to note, so this is the protoplanetary disk, right? And this bulge here is actually what they observed to be moving. So the star itself is very young. It's about 12 million years old, so it's like 1% of how long our star has been around. And yeah, they've been observing these massive blobs moving at incredibly high speed, moving through the protoplanetary disk. And what's kind of happening is that it's pushing it out. The fear really for these stars is that the raw materials that you would potentially need for life really they will be gone. So all these water particles and dust and everything like that is just going to get swept out by these giant blobs. This analogy I thought was pretty good. They're basically acting like snowplows, just pushing all this stuff out of the way. Based on their observations, they estimate that in this case, this particular red dwarf, the protoplanetary disk could be gone in about 1.5 million years, which is really short on astronomical timescales. Like it's nowhere near enough time to start forming planets and the like. They don't really know what the blobs are or where they come from, but they've got some neat dynamics and patterns to them that they can observe over time. So we've got these loop-like structures in here. So they're pretty excited about that and looking around and seeing what they can find there. Item 3. I'm cheating a little bit because there's going to be a lot of sub-items within this item, but it's a grand-ish tour. There's been a lot of planetary exploration lately, and my usual go-to for planetary exploration stuff is the Planetary Society. They've got a phenomenal website with some really good writers. I recommend checking them out. There's a lot of really... Emily Lactabala is actually probably one of my favorite science writers out there today. She does a really, really good work on planetary science. It's worth checking out the website. And basically that's where I got most of this content from. So, we did talk about the Mars InSight landing. So this is a probe that they sent to study the seismic activity on Mars. And that right there is the seismometer. Now they've got other instruments. They're going to be drilling in and digging down to put a heat probe in there. This is always neat, getting to see some form of animated thing going on a different planet, right? So they got this little crane here, and it's bringing it down and dropping this thing down. In a subsequent animation, this thing will, which I don't have actually, but this thing will basically put it down all the way. Excuse me. And then this detaches, and that will be the seismometer that they use. Fancy technobabble. What I thought was neat was that they use this they've got this sundial for azimuth, so they can orient themselves. Kind of neat. Know where they are. And what time of day, and what time it is as well. So, so they're making good progress there. They're still, getting things online and moving along. But Osiris Rex, which we had a presentation on, I think, two years ago, to this month actually. So there's this, so basically we have this spacecraft now orbiting a little rock that is covered in a bunch of other little rocks, which interestingly enough has presented some challenges for them, and this might be a challenge for other sample return, is there's not a lot of good places to set down on this thing and try to collect some dust with. You have all these big chunks floating around here. But they're going to spend a lot of time looking at this. So this is from an altitude of about 2 kilometers. It's about as tight as they're going to get before they start making their runs in later on. So this is their timeline. So right now they're in this preliminary survey, and then they go through various orbits and do detailed surveys, recon, which I assume is when they're going to really go for their landing for attempt to do sample return. And the rehearsal will be in December of 2019. So 12 months from now, they're going to make an attempt at it. Well, not really, not a real attempt, but basically to see if they can actually get in there or not. And then later that's in the following summer, they're going to try and collect some sample off the surface of it. So look forward to that. And then it's going to come back to Earth. Yeah, and then meanwhile, way on the other side of the moon, I'm probably going to butcher this, but Chang'e 4 made its way onto the far side of the moon, and they got a little rover. So the Chinese, I don't know what their actual title is, but China's space program landed this successfully on the far side of the moon. It's a first. They're going to be going around, trying to do a little bit of science, looking at seeing if they can find frozen. I think they're trying to get into the craters near the south pole, and seeing if they can find frozen water. If you're curious to know where they're located, right there, right. This is the side of the moon that we're never used to seeing. I always thought it'd be kind of neat if this had been the side of the moon. I mean, I know why it's like this, but if this had been the side of the moon that we could have, viewed, there's a lot more going on there. But anyway, but yeah, so it's in this crater. If you want a zoomed-in version, it's the Von Karman crater, and they're right there. I regrettably don't have a scale on this, but yeah. So they're going to be out there for a little while and roving around. And of course, the big one, New Horizons, is at the Cameron Object 2014 MU69, or as I like to call it, Mr. Peanut. Co-worker of mine put that together. So the New Horizons spacecraft made its way there. They got all they did a count of all the images that were collected, and everything came back good, and now they're just waiting 20 months or whatever for it to come back. There's actually been quite a lull in the data coming back because right now I think the spacecraft is somewhat close to the sun for a little bit of time, but they should be getting, well, in view of the sun, I should say. But they should be getting data back soon.
Only after the U.S. government reopens.
Yeah, that. Right. I forgot about that. Yeah, there was that whole shutdown thing that happened. We should try that sometime. That'd be fun. RASC government shutdown. Yeah. Okay. But if you don't know where this thing is, so this is a view of it, way off way up the actual plane, because Pluto has a tendency to do that as it flew by. This line right here, Pluto would have been right there, because that's where they crossed and continued moving on. This is just another view of it. It's quite a long ways away, but it got some fantastic. They already managed to send back some pretty fantastic data. This is not one image; it's a composite. But there are these are the approach shots. Right? This depression here, I think, is really interesting. Now, the thing about this object is that it is a contact binary, right? So these are actually two objects that are touching each other, right? And they basically said this is effectively the theory to how it formed, where you get this chunk of stuff, and then they form these two bodies, and then the two bodies rotate around each other, and then contact. And finally, Cassini at Jupiter. So this is a shot of a beautiful shot of the Cassini probe, which is now in pieces scattered across the atmosphere of Saturn, through the atmosphere of Saturn. But when it was flying by Jupiter, it took some amazing pictures, and this was one of them. Now, one of the things that people kind of forget about is that there's actually a wealth of data that NASA has that doesn't really get looked at all that much, and a bunch of amateur image processors out there have done a really tremendous job of going back through this data and pulling up some really cool stuff. So this came up recently. We'll see if it plays. Yeah, there we go. It's breathtaking. You feel like you're there. It's absolutely incredible. So that's Io. That's Europa. Yeah, I know. So it's an incredible team. Not team, but just an incredible group. There's these people that are going back through the NASA archives and digging up this data and doing a bunch of really cool image processing on it. Yeah, just tremendous stuff. Anyway. But yeah, that's all I had for what's new. We'll move on to Brian with what's up in the next guy.
Brennan, I apologize that earlier. Okay, so what do we have up for the night sky? We'd be kind of brief. The election coming up. Okay. Okay, so what do we have for planets? Not much happening. Unfortunately, we lost Mars. Where'd it go? So Mars is out of the question. We still have Jupiter. Well, Mars is still up in the sky, but not much. The viewing part of it is kind of out of the question. Mercury and Saturn are too close to the Sun to be observed. So let's move on. This is me trying different transitions. Okay, so what do we have here? We have Jupiter and Venus, I believe, right? So that's tomorrow. That's what's going to happen early in the morning. Okay, there's the Sun up here. Of course, Saturn is just too close to the Sun to be observed. Okay, what else do we have for planets? We have, of course, in the evening still, we have the Moon and Jupiter. Sorry. Am I a little too far? That was supposed to be Mars. I made a mistake here. That's supposed to be Mars up there and the Moon. Like I said, Mars is still observable in the evening, but unfortunately, I made a mistake there. It's a typo. Okay, now this is January 31st. So we have the Moon, Jupiter, and Venus early in the morning. The Sun is over here. It's just too close for Saturn and Mercury to be observed, but it's interesting that we have all these three early in the morning around about 7 o'clock in the morning. Hope I changed it. Okay, there we go. Okay, for the main events that's happening this month, we have the lunar eclipse coming up. And do I have the date right? Because I had it wrong one time. Okay, the 21st. The 20th? Yes. Oh, God, I didn't change it. Okay, sorry.
It's the 21st UT time.
University time, that's where I got the
That's right.
I apologize for that, sorry.
The end of it's on the 21st.
21st, okay, so.
Sunday night.
Read Win-Eccentrics.
Actually, I did a little bit. Anyway. Okay, I apologize for that. This was the 20th. I thought I changed it. I saved it a number of times, but unfortunately, yeah. So it's on the 20th, okay? Okay, so on the 22nd, I guess the Winter Secretary did mention about Venus and Jupiter being close to each other. And of course, I mentioned about January 31st. Okay. Sorry, 21st come up again, so.
You gotta get on the right.
That's right.
Take 6 hours.
So it's January the 20th, sorry. I apologize for that. Okay, well actually no. I do have the 20th and the 21st, you know, so I do have it right. The reason why I put this here, because last lunar eclipse we had was pretty close in the morning, I think it was like 6:30. And the main event didn't happen until after it set. So yes, everything is observable. It's actually a good, decent time. I don't know what the forecast is. I haven't looked at it, but if it's good, or it's not too cold, I might be hosting it at Glen Lee, if it's if the weather is being enforced. What do we have next? I used that too many times that way. Okay, what's interesting about this lunar eclipse, and probably will have lots of phone ops for people who have cameras, we have the moon there, and of course we have the Beehive cluster. When I was playing around with the simulation here, that's probably when it's the main eclipse right there. That'll be the closest point to the Beehive cluster. So that will be interesting if, of course, weather is permitting. What else do we have? Okay, so that's, like I said, it's a lunar eclipse, and of course, that's the Beehive cluster in 44. moving on. Okay. What do I have here? This is a little simulation. Oh, didn't flip. Okay, it's not working. Okay, this is supposed to try and give you an idea. As the Earth is rotating, the lunar eclipse is moving towards the west here. So anyways, that was supposed to be a little simulation, but it's not working right now. But this kind of give you an idea about the time frame. So it's full of 5-hour eclipse here. We do get very few chances of actually seeing a good lunar eclipse during the evening. Okay, this is just a quick simulation about how it's going to look like, especially for the new members. Again, let's see if this works. Better work. Okay, it is working finally. All right, just kind of give you an idea. Okay, so we're entering the shadow of the Earth, and then just kind of give you an idea for the new members that haven't seen the lunar eclipse, and then you get the red moon here, or the blood moon, as some people are calling it at one point. So this is sped up. Of course, this is a duration of about 5 hours. Hopefully, it's not too cold. Last time I had around this month, was it December, I think? Yeah. I was helping Ron, who was president at the time, and it was freezing cold that time. But it happened around 8 o'clock, I think. Can't remember. It was at the forest we did. Okay, so that's just to give you an idea of what the lunar eclipse is going to look like, weather permitting, of course. So let's run through it one more time, and then we'll move on to the lections. Last time I was able to see the back of my house, which is pretty nice. Okay, all right, that's all I have to say for what's up in the sky. Thanks.
Yeah, the lunar eclipse we had last year, I observed very comfortably from my dining room window. It's pretty chilly out. The lights are going to be turned on, FYI. Yeah, forget your dark shadow.
Well, once a year for 15 or 20 or 25 minutes, we have to do business. And this is it. And the nomination committee, which consists of me, spent 6 weeks searching for candidates for the various positions on our council. And everything in here is virtually black and white, so we don't have to do too much about turning colleagues down. Let's go over who's in charge now. President Brandon Petrasek, Brian Pack, Vice President, Secretary Cliff.
He's on call tonight, he couldn't make it.
Okay, that's right, I remember you told me that. And Treasurer Stan Run. He's in the house, but he's hiding behind a magazine there. These are the people who do most of the work. And I think we should all owe them a hand. Thank you for everything they've done. We also have counselors who join us at the meetings to drink beer and eat the chips and offer advice and do some of the smaller bits of work. Ralph Croning, where are you, Ralph? There he is at the back. Mick in the middle. Paul, there he is. Megan, is she here tonight? There she is, also at the back. All the counselors hide out in the back. And Kevin. There he is. An interesting thing happened on the way to the forum. all of these council members are up for replacement, and they cannot run again themselves, or they've chosen not to. So we need 5 new councilors. We need a new president, we need a new vice president, we need a new treasurer. But Cliff is staying on for another term. Terms are 2 years with 1 repeat allowed, so you can be on council for 4 years in a row, and then you have to sit out 1 election cycle before you can. But it also brings up a problem, is that next year we'll have to, well, 2 years from now, we'll have to elect the whole council all over again. So I have arbitrarily picked 3 councilors and 1 executive member after consultation with myself. Actually, with the rest of the council, I said, I want to do this, and nobody answered, so I take that as tacit approval.
I believe I said okay.
Yeah, you said okay. But arbitrarily determined that 4 of the positions would be for 1 year, so that we can get back into leapfrogging in our selection of council members. I think we should give these people a hand for the work that they've done for the past. Well, as lead member of the nominating committee, it's my job to come up with nominees. But we also have appointed positions for which we require volunteers. We have a national rep who attends either in person or via Skype the national meetings and keeps a track of what they're doing, and also represents our interests in the things that National's doing. And Dennis Lyons has been doing that for us for several years now. Dennis? There he is at the back. Mike Caracas and Abdul Almani have been looking after Winnicentrics, the little newsletter. I did it for the issue that you have now, but we'd certainly like to have somebody who has hankerings to get into publishing or writing or just running the journal out of the goodness, or the Winnicentrics out of the goodness of their heart, to let Brendan or the new president know, because it is an appointed position, so council basically votes to accept a volunteer. Now, Winnicentrics is produced in Microsoft Publisher. It makes it easy for people who can just take the template, but there are also alternative public programs that will run publisher files, so you don't have to have publisher. Most people who have Microsoft Office will have publisher. Sprucewood Star Party organizers, Sylvia and Cliff. Sylvia, somebody gave me a little caress. Oh yeah, there she is. She just went past me and I got a pat on the back from her, so I knew she was here. Cliff, of course, is not here. Sylvia is looking for somebody else to take over the Sprucewood Star Party. And I don't know if I should say this, but a woman with whom I'm very familiar has thought she might do it, but we'll see what happens. I'll try persuading her tonight. Kevin McGregor, is he here tonight? Kevin is our webmaster. Kevin is yet to make an appearance at a meeting, so we'll probably have to see what the new organizing committee can do. And Brian Stach, who you know, is the observatory director. Fine job's been done on the observatory in the past 2 years, but he's put in all kinds of new equipment and kept this place running. If you haven't been out to the observatory and haven't picked up a key to go out, you should, if for no other reason, on a Saturday afternoon in summer to have a picnic out there, because it's a nice quiet place with nobody to bother you. Nobody's going to be there in the middle of the day, so it's kind of a getaway in the summer day as well as a place to go at night when we get the stars. So I think we should thank all of the volunteers, many of who are staying on for the work they've done over the past few years. And sometimes they attend the meetings and drink the beer, and sometimes they don't. So here's what we need. President, vice president, secretary, a treasurer. Well, secretary we don't need. We do have to vote on it, but Cliff has allowed us how he's going to stay on for another term. All the counselors and the Winnicentrics editor will be looking for volunteer afterwards. So let's begin. Nominating committee. I've already been through this. This tells you what the terms are for each of the positions and why we're going for some one-year positions. And depending on the results of the elections, the people who've been randomly assigned one-year positions might change. To begin with, I'll introduce the candidates that we picked and persuaded in the nominating committee. Then I will accept nominations from the floor for those positions, and if necessary, we'll have a vote. I prefer that candidates nominate from the floor be willing to serve. Don't nominate somebody and then leave them with the position of having to say, no, Cliff, you are here tonight. Wait a minute. I just got here. So, let's go through this process. President, current vice president, fellow you just heard, Brian Stach, has agreed to move up into the president's position. Do I have any other nominations for president? I might add that the councilors who've agreed to serve have all universally said anything but president or vice president. Once again, do we have any nominations for president? Brian, you've been elected by acclamation as president. Congratulations. Vice president. Dennis Lyons has agreed to stand for 1 year as vice president. This will be one of the terms that goes into leapfrogging. Dennis has been fairly active in the background. He's been the person who's been representing us with the folks from the Nature Conservancy about establishing a dark sky site to the southeast of Winnipeg. And he's been our national rep, and he's been on council before in past years. Do we have any other nominations for vice president? Once again, any nominations for vice president? Congratulations, Dennis, and thank you very much. Treasurer. Dan Rund has indicated that he would like to cease being treasurer, and Abdul Almani has volunteered to take on that position. Now, Abdul is the one who runs cameras every day for us, and he's been on council in the past. Abdul is sitting beside the camera. So I hope if you're elected that you continue to do, or even if you're not elected, to continue to be our videographer. Do I have any other nominations for treasurer? Are there any other nominations for treasurer? Congratulations and thank you, Abdul. Secretary, Cliff Levy is agreed to stay on as secretary. In fact, Cliff has not been secretary very long because he stepped into vacant positions, what, a year ago? 2 years ago?
It was about, I think we went about 6 months with that.
Are there any other nominations for secretary? Any other nominations? Thank you, Cliff, and congratulations. I have 6 nominations for 5 councilors, so we will be electing councilors at this meeting. Do I have any other nominations for councilor? Sam Giesbrecht, are you here? Sam was a late addition to the list, so I didn't get to see very much of him. Karen and Ed and Sam are all relatively new members to the RASC with 1 or 2 years experience. But they have background experiences which will prove valuable on council. Darren Henning, you've met. You can talk to start this session. Bill Crosney has not been active in council for quite some time, something about raising kids. But Bill has been very active in the past and has been very active in Edmonton as well. Lots of experience with the RASC. Gordon Tulloch, you've heard of before. By the way, is Bill here? There you go. How come you guys are all sitting at the back? Maybe I should go through the others too, and I will. Gordon Tulloch is given a couple of talks. Gordon is a long-standing member who sort of moved too far away from the city to attend these meetings, but now has been coming back. Gordon, are you here? No, he said he wouldn't be here tonight.
He's at the Jets game.
Yeah. At the Jets game, right. Karen Anderson, are you here? Here's Karen down in front. Ed? Ed over here by the camera. And Darren. And Darren, of course, we've all seen Darren tonight. So we've met everybody. Any other nominations for council? Any other volunteers for council? Theoretically, every nominee should have 2 members signing for them, but we're letting that go. All right, we'll leave this up here. Give me a hand and pass these out. I think we'll have 1 ballot each, or 1 ballot for all 5 names. Just pass one of those around.
Members only.
More than once. This is not the
Jay?
Republican Party of the United States.
Jay, members only.
Oh yes, members only. If you're not a member, you get to applaud. Pencils. I don't know how many of these pencils work, but I'll put them out. I have been instructed not to bring these pencils home. We have so many of them around the house. Some of them might not. You can just put down initials if you like.
Thank you.
5 out of the 6. Here, pass it back. Anybody, any row need pencils? You're voting? Pick 5 out of the 6. You can put initials down, and we'll collect them and count them over the break. Any more pencils needed?
Mine's not working.
Okay, I'll be over there. We're good? Oh. Well, we need some more ballots. Fold the ballot in half when you're done, and I'll send along a bag to collect them.
Oh, he's sticking around. Nothing to do with the more official courthouse of water costs.
Yeah, the bank says free-range chicken on that. Not a,
No, it's voter suppression here.
Hire something on that. You got it.
end of your pen.
Does anyone still need ballots? Do you want to vote twice? Or really vote other people?
Okay, I'm going to count the number of people here today.
I voted for Gordon twice.
Yeah, so if you have voted, your reward is you get to go for refreshments. We'll meet back up at 9 o'clock for our main talk. That'd be great. All right. Welcome back. I hope you enjoyed participating in your civic duties and enjoyed the refreshments. Okay, so I have the list of winners. I want to give everyone a chance to settle down a little bit. Alright, in no particular order, our new counselors. Karen Anderson. Congratulations. Ed Wright. Congratulations. Sharon Hennig. Congratulations. Bill Crosby. Congrats. And hopefully I don't butcher this, Sam Giesberg. Also, congrats to Gord, who's currently at the Jets game. He won't be a counselor, but he's currently watching them trash the Red Wings 3-1. we will likely, I don't think Gord will be too disheartened, and we will likely see him on council at some point in the future. So, but thank you very much to everyone that came on and volunteered. And yeah, so but I did want to say a couple words. It's been a really fun 2 years. I have really enjoyed doing this president thing. Don't get me wrong, it's a lot of work, and it's a real challenge. I've now seen how the sausage is made. It's actually not that ugly though. It's a lot of fun. You work with a lot of good people, and you get to contribute in a way that I think that really matters. We've organized a lot of public observing events, done a lot of outreach, and we are just incredibly fortunate to have an incredible group of people. Jay talked about all the various positions. One of the things I did want to mention is we also have the kind of people who will bring snacks and goodies. Most of this is organized by Gail, so thank you, Gail, for giving us a refreshment every night. You stepped in. Stan, you want to interrupt me?
I just want to point out that Gail was also one of the councillors from the last term. Her name
Yes.
got kind of missed.
Yes, and thank you, Gail. Your name wasn't up there, but thank you. Thank you for being one of our fine councillors. Yeah, so anyway, this is the last time that I officially get to do this as president. What I mean by that is I'm going to be introducing somebody. But I want to say thanks. Thanks to the club. It's been a lot of fun, and I'll probably do it again in like 10 years or something. Yeah, thanks. All right, but moving on to our featured presentation. Our guest speaker tonight hails all the way from the University of Manitoba. She's in the active galactic nuclei group. She's got a keen interest in fairly deep knowledge of astronomy, from telescope making to cosmology. She has a background in nuclear and particle physics with industrial work experience. I was treated to some of this when she mentioned that she worked on the Chime project and was showing myself, and actually my parents are here tonight, by the way, so you can thank them for me. They're from tomorrow, so they actually drove out for this. But she was showing us a lot of pictures and video of the Chime instrument, and now I'm kind of tempted to maybe get her back for a talk on Chime, but we'll negotiate on that later at some point, or you can talk to Brian. Anyway, but instead of Chime, tonight Michelle will be talking about the dark universe. So if you could join me in welcoming Michelle Boyce.
So I'm Michelle Boyce. As Brendan mentioned, I worked at McGill University on the Chime telescope as part of a 2-year contract. And I was involved in some of the systems design and software development and databases and so forth. And now I'm working at the University of Manitoba in their active galactic nuclei group, putting together databases of multi-band data from different radio surveys, optical surveys, ultraviolet surveys, and so forth for studying active galactic nuclei, as well as other objects out there. This is a talk I gave. Actually, I was going to give a talk on Pluto for the University of Manitoba Open House, and like 2 weeks before they said, wait, that's Halloween. And I said, oh, okay, fine, Pluto's not scary. So I decided to do something dark. So I went with black holes, dark matter, dark stars, and there was a whole Halloween theme. So I've actually removed all the Halloween goodies from it. Halloween is also Dark Matter Day. So it was full of Easter eggs, Death Stars, and shadow ships and so forth. Yeah, and I was dressed as a Minbari Anyway, so I'm going, this talk is sort of targeted to the public, but it's also targeted to inspire people because it's for a broad range of people, so it inspires kids and stuff like that. So you'll find some stuff really interesting, some people find some stuff really interesting and some stuff too detailed. But there's no math, there's no integrals or anything like that. It's just, but as my background is particle physics, you're going to get a bit of a shock on that. But it's just your basic hydrogen atom that I'm going to use, stuff that you're familiar with. Okay, so what's that? What was that movie of? Well, let's look at this. Basically, this is a Hubble view, and this is a mapping of the dark matter. And that was just a rotation of that image. And if you don't know what dark matter is, actually we actually don't know what dark matter is, but if you don't know what it's all about, well, by the time I'm done, you'll have a good idea of what that is. Okay, so here's the overview of the talk. And basically, currently, right now in our universe, believe it or not, everything that we can see in terms of interstellar gas, stars, planets, yada yada, is only 5% of what's out there. And the rest consists of this strange stuff called dark matter and this more recent stuff called dark energy. So I'm actually going to spend time going behind the theory to understand these things. So I'm going to include other dark objects like black holes and dark stars. So what I'm going to do is I'll give you a bit of theory and then talk about, say, black holes, for instance, then a bit more theory of gravitational lensing, particle physics, and some Big Bang theory. And I'll go through each of those to give you a sense of how, in terms of cosmology, that large-scale objects are affected by small-scale things. It's actually quite fascinating that stuff we do in the lab at accelerators is very pertinent to what's going on out in the universe. So I hope that inspires some people. So let's start with the rubber sheet analogy of general relativity. Some of you may have played around on the internet. You'll find this like 15-minute video. It's a very fascinating video where this, I think it's actually taught, it's at the school, and there's this big drum with a rubber sheet. They put this large mass in the middle, and that mass represents the distortion of space and time. The problem is, it's really in 3 dimensions. You kind of have to think about that when you stick the Earth in there, it's displacing space all around in 3 dimensions, as well as time, which we're not really going to get into as much. So that displacement, these lines to light, these lines look like straight lines. It doesn't know that it's being curved. And when you take a lighter mass and toss it in here, you can actually get an orbit, a collision, or even just escape, parabolic escape. And this demonstration that guy does that, he throws in civil moons and stuff. It's actually quite fun to watch. Okay, so that's general relativity. But how do we test this theory? So one theory was, one really good test was the Eddington expedition in 1999 where they were looking at a solar eclipse. So what they did was, they looked at measured stars in Ea and their positions precisely, and they knew at the time of this eclipse that the star, one of the stars would actually be behind the sun, right? Here. So if Einstein's theory of general relativity was true, their calculations were true, they should see the star appear as it was here. So this is the light, and when you look back, it appears to be coming from here. So they did this experiment and indeed found that there was a star there that corresponded to this star that shouldn't have been seen. So that was a verification of general relativity, at least part of it. There's many other famous verifications, such as the rapid precession of Mercury, orbital precession. So there's this effect that you can use. You can actually do something called gravitational lensing. So if you have a large enough object here, and this is your line of sight, and there's something directly behind it, the light from that would get bent around like so, and when you look, you would see it back like this. And if it's perfect enough, it'll show up as a ring. And if you want a perfect lab to mimic a gravitational lens, break off the bottom of a wine glass, and that shape will actually give you the same effect, and you can slide it on paper and see these cool effects. So these are many Hubble Space Telescope pictures, and this is the Hubble Smiley. This is the only Halloween Easter egg left over, by the way. Yeah. Oh no, there's one more left. Okay, yeah. Yeah, so that was a Death Star. Okay, some more obvious, some weren't. So the other one that you've heard of are black holes. Now, this is the extreme limit, and this is a limit in the theory where you get so much mass that you get what's called a singularity. As a physicist, the singularity is a point where the theory breaks down. And so that means to me that to better understand what's happening there, you would have to have a theory that includes particle physics, quantum mechanics, and gravity all in one, which we don't really have at this point in time, or nothing testable. So, so if we look at this, even light can't escape. So here I'm showing these light trajectories, and as you get closer and closer, you can actually put a light beam in orbit, and that is referred to as the event horizon, the point of no return for anything. Everything and anything goes down into that black hole. Okay. So no light comes out. So how do you see black holes? Well, you see them indirectly. So this is an example here, and this is related to work that's done in our research group. In fact, Chris O'Day is my supervisor. Chris O'Day. And what we're looking at here, this is a combined radio-optical image. And this purple color here represents jets that you see in the radio. And here is an optical image. So over on the right here is sort of a theoretical model. And what happens is that in the center there's a black hole, and gas is being spiraled into the black hole. And as it gets closer and closer, it gets more and more squeezed, and then starts to ignite and give off energy. And at some point, if there's too much mass going in, some of it gets spit out like this as high energy jets, which are visible predominantly in the radio, I think also in the X-ray also. Yeah, so, no, not the X-ray. These are definitely in the radio. So yeah, this is basically the mechanism and the indirect evidence showing the existence of black holes. There's also Sagittarius, A star, the center of Milky Way, and you watch. There's an episode on how the universe works, and it's actually quite fascinating. It shows how rapidly stars are going around. One of my favorite episodes, by the way, is How the Universe Built Your Car. That's pretty cool. So, it tells you how all the elements were made. Okay, so now, so at this point, I went on to explain some particle physics because I needed it to discuss topics in dark matter and give you an idea of how complex it is. So that was a whiteboard thing I did. It was actually less intimidating on the whiteboard. So what I'm going to do is I have a couple of slides just to introduce you to what we know of matter today, of what it is. So let's just look at this carefully. So this, you just imagine this is a dark blob right now, and you have an electron and then a nucleus. And the hydrogen atom is just one proton and one electron, which orbits around it. In order to get more of a complete picture, I've added an extra neutron to the nucleus. So you have a proton and a neutron, which is a deuteron, okay, or deuterium, it's a deuterium. Which, by the way, heavy water, instead of having hydrogen, is H2O, it has H2D. Okay, so the atom, which consists of nucleons, which are protons and neutrons. And the electron has a negative electric charge, and it's attracted to the positive electric charge of the proton, which you're familiar with electrostatics in high school, or rubbing balloons on your hair and sticking them to the ceiling. So that should be familiar to you. What may not be as familiar is that what mediates this interaction is referred to as the photon. And the way I like to visualize that is if you have two boats moving along in the water, they have waves, and the waves between the boats cause them to interact. And depending on the interaction, it could be repulsive or attractive, or none at all. So you can imagine the waves, and then you can imagine all the water droplets as the particles that make up those waves. So an exchange of one water droplet between them, you could think of that as a photon, and then the whole thing is a collection. So basically, it's sort of a wave-particle duality explanation, very crude explanation. So you have a mediating particle, and that's the photon. So this is known as the electromagnetic interaction, the electromagnetic force mediated by the proton, electron charge 1. Electrons belong to a family of particles known as leptons. And they carry electron number of 1. Okay? So it's just the quantum mechanics has numbers that describe things, and this is like a quantum number. It says this particle has this property called lepton number, which is conserved. Okay? So the electric charge doesn't change, so -1 is actually the fundamental electric charge if you've done Millikan's experiment. The nucleus consists of protons and neutrons, and those protons and neutrons are made up of these constituent quarks. And in our case, for the proton, we have 2 up quarks and 2 down quarks. They carry charge 2/3 and 1/3 each, and if you add that up, that gives you the charge of the proton. And of course, the question is, well, I thought you said charge, that's the fundamental charge, which is true because you cannot get isolated quarks. So, hopefully this is all good. So here the mediating force is the gluon, and as opposed to electric charge, okay, they use a charge which is a chromodynamic force or a color charge. So they have, the quarks can have 3 charges, red, green, and blue. And depending on those combinations, depends on the force and the type of force. So this is just to give you, pardon the pun, flavor, which stands for these up and down are the term flavor. So up, down, the flavor of the quark. And then you have the color charge. Now the quarks carry, this is an important quantity, remember, the quarks carry a baryon number of +1/3. So the proton has a baryon number of 1, the same as the neutron, and that's a quantity that is also conserved. So anything made up of protons and neutrons are referred to as baryons, or baryonic matter. What else? So yeah, so that's the basic nucleus. So the quarks here are the most fundamental particles we know. We've broken matter down to this point, and we haven't seen anything else yet at the scales that we've looked at. So this is how we understand things today. So this picture's not quite complete, but let's first, before we go on, let's get a sense of the scale of things. So this diagram is, there's actually a website here, and there's these posts, there's infographics, and this is just from the center of the infographic. It's all this information on it. And so this gives you the size of the components in the atom. But what I like is this sentence down here. If protons and neutrons in this picture were 10 centimeters across, the quarks and electrons would be 0.1 millimeters, and the size of the entire atom would be 10 kilometers. So that just gives you an idea of the scale of things and how much space there actually is in an atom. Okay. So moving on then. So we've talked about photons and gluons. Are there other mediating particles for different forces? So photons mediate the electromagnetic force, and gluons mediate what's called the strong force. So let's look at the nuclear decay process. So now that we have a bit of a vocabulary here, This is a neutron. A free neutron in about 12 minutes would decay into a proton, electron, and antineutrino. Why antineutrino? Because antineutrino has a -1 lepton number. Electron has a +1 lepton number, so the lepton number of this is 0. So it's conserved, because these have no lepton number. So this is actually a conserved quantity. That's why it has to be that way. That's just the way it is. We observe things and we put labels on the conserved quantities. So when we look at reactions. So here, what's happening is, here's a neutron. It has 2 downs, -1 plus -1, which is -2/3, plus enough, which is 2/3, which gives you 0 charge. But the proton is a charge 1, so we have to add 2/3 charge here to get this to be a proton. So charge, the electric charge is conserved, so we take it away using what's called a W- particle. I like to think of this particle as a heavy photon. It's a photon with a lot of mass. Photons have no mass, but this is a heavy photon, and they come with charge plus, minus, and 0, which you'll see shortly. So if you add up the numbers here, everything all adds up. And also baryon number is conserved. The flavor is flipped, but that's related to a symmetry, which I may or may not explain a bit later, which I remember. So that's the basic thing here. And this W mediates what's called a weak force. So if you look at this up and down, in terms of symmetry, it's actually looked at as one particle in this force. And the same here with the neutrino and the anti-electron neutrino. That's important to remember that there's different types of neutrinos. This is also seen under this symmetry as one particle. So this is actually a force between these two particles. Okay, they're just changing their state because of this. So the conserved quantities here are electric charge, lepton number, baryon number, and spin. Particles have an intrinsic spin, which is basically an angular momentum, and it's in the context of quantum mechanics. So it's in that context of symmetries. So this is neutron decay, or sometimes called beta decay. Historically, when they saw this charged particle, they didn't know what it was, so they called it a beta particle. Okay. So let's now slap down the entire standard model of particle physics, all the particles that we know as of today, and that we've discovered. The most recently was the Higgs boson that we've discovered. The Higgs boson is an interesting particle because it's what gives mass to these particles. Without this, all these particles would have no mass. And the way to look at the Higgs boson, for instance, you look at light. Light has no mass, but if it travels through a piece of glass, it actually slows down. It slows down because it's interacting with the glass. It's interacting with all the atoms and the charges in the glass, so it goes slower. So that you can think of it as having an effective mass, because now it's going less than the speed of light, and only massless particles can do that. So the Higgs is the same thing. In the vacuum, space-time vacuum, the Higgs actually gives mass to some of these particles that are trudging through the vacuum. So we talked about the up-down quark and the electron and electron neutrino, this family here. And notice how they're complementary. Charge plus 2/3, minus 1/3, charge minus 1, charge 0. So there's that complementariness to them. And I've given here a list of the masses. Physicists like to measure mass in electron volts per c². They also like to set the speed of light to 1, so sometimes they just say eV instead of eV per c². But this gives you this idea that, for instance, the electron here is half an MeV, and so that means it weighs 10 to the minus 30 kilograms. It just gives you a nice idea of the mass. So you have these families here, up, down, charge strange, top, bottom, and then muon neutrino, tau neutrino, and the antiparticles. And then you have these mediating particles. So we looked at W. There's a W plus minus and Z naught, and these are the intermediate gauge vector bosons, to add more technical terms. And I call these heavy charged photons. And you can see they're quite massive. They're actually in GeV scale. They're a factor of 10 to the 3. And the more massive these things are, the tighter range they are. So, so this is the standard model. So these represent the weak force, strong force, and the electromagnetic force. And those, besides gravity, are all the fundamental forces of nature. This entire model is consistent. It's been tested, and so far it's proven quite well. The last thing discovered, as I said, was this at the CERN super collider, and now they're looking for other particles, which I'll mention shortly. So, just as an application of this, we'll just stick in the light universe. We'll do one example and move on back to the dark universe. So here's the proton-proton production in the sun that produces helium. So here you get two hydrogens, and basically the sun is so dense. This happens in the core. They fuse into what's called deuterium. And then you take deuterium and another hydrogen, and you get helium-3. Then you fuse that, and you get helium-4 and 2 protons. Basically, helium-4 has 2 protons in it and 2 neutrons. So if you do the bookkeeping, you'll be able to figure this out. The byproducts are light and neutrinos. And I have a little analogy down here. Right now, if you took your thumb up to the sun, well, wherever it is, you would have 65 billion neutrinos passing through you per second, and 10 million times more photons bouncing off your thumb. So that just gives you an idea of how much of this is coming out of the sun. Interesting thing about neutrinos is they rarely interact or hit anything. They could travel through a solar system of lead before they hit a single lead atom. That's how weakly interacting they are. So when I say weakly interacting, that means these are particles that are very difficult to see. You need a large tank of water, and maybe in a month you might get 1 or 2 hits. So some of you may have heard of the suburban neutrino detector. They get 1.5 neutrinos per month on average. So let's just take a quick look at this process here where I'm creating deuterium. So I take 2 hydrogen atoms and essentially just strip away the electrons. These are basically 2 protons that I have sitting here. And what I do is I need to change 1 proton into a neutron, so I flip a upward into a down, and I have to conserve my charge, so I spit out a W, and I spit out a positively charged electron, or a positron, or an anti-electron. Okay, so that's the anti-particle. And I spit out a neutrino, and this time it's not an anti-electron neutrino, and again, electron numbers conserved. So this is sort of a blow up at the fundamental scale of what's happening here in terms of quarks. Okay, so this is basically a weak force, the process that's happening here. But the distance of this force is within the length of this nucleus. Basically 10 to the minus 15 meter. That's the range of this force. So So for this to happen, you need extreme pressure and temperature to get that reaction to happen. That's why the sun burns slowly. And once it's burnt up all helium, then it starts burning the other stuff and so forth. Okay, so that's it for particle, well, almost it, but that's it for the basic matter as we know it. So let's move back along now and ask ourselves, well, why dark matter? Now, there is an entire history of dark matter, and I'm really certain quite a few of you are familiar with like Zwicky's observations of stellar drift and so forth. But I found that this one is, I think, the most intuitive one, so I put this down as an example instead of going through the entire lengthy history. So, if we take, assuming we knew nothing about dark matter, we didn't even know it existed, if we just take a spiral galaxy like this, and we measure the rate of the stars and how fast it's spinning and so forth, what we would expect is that as we go further out from the disk, it should slow down. Not unlike when you have water in a sink and you unplug it and you can see it makes a tornado. It's faster in the middle and slower on the outside. That's what we'd expect. But what happens is it's actually increasing. And the only way we can seem to account for this is that, well, there must be matter that we can't see that's also contributing to this. And if we do various mathematical models, what we find is that there's a halo of matter that we don't know what it is that's required to give us this curve where it's actually still increasing as we move outwards from the center. Okay, so this is what we refer to as dark matter. So the question is, well, actually, didn't quite get to the question. I'm still on why dark matter. So here's another way of looking at dark matter and an application of gravitational lensing. So this is April 1689, and if you look very carefully, you'll see there's a little arc there, a little arc there. You see that? There. That's gravitational lensing effect. So what that's telling us is that there must be some huge mass in here. This is sort of an analogy what we're looking at, and this is the gravitational lens forces that we're seeing. And again, we do a similar type of math. We find that the blue splotches here, this shows us the distribution of dark matter within this cluster. So there's some other unknown matter that's in there that's causing this. Okay. Another example is the kids survey in the Virgo cluster. And basically they looked at all the stuff in this cluster and mapped out a dark matter density map. So this is basically what it looks like. The other thing about the interesting thing about the structure of dark matter is it almost looks like a spider web. And where the webs meet, that's the densest part, and that's where the galaxies form. Okay? And so you kind of get this bubble structure. Okay, so if you've heard of baryon acoustic oscillations, that's kind of where that comes from. I don't know if people have heard about that for cosmic microwave background searches, but and now you know what the term baryon means. It just means regular matter. So yeah. So okay. So we say okay. So there is dark matter. So what is it? What is dark matter? Is it macho? Are they massive compact halo objects? Massive compact halo objects are basically things that we can't really see, and it's referred to as baryonic matter because it's made of protons and neutrons. So made of stuff that we know, such as brown dwarfs, white dwarfs, supermassive black holes, or that aren't inflating, or stuff like that, or primordial black holes. So these are all macho candidates. Or is it wimpy? Weakly interacting massive particle. Remember when I said that like a neutrino could pass through a solar system of lead without hitting anything? That's weakly interacting. Okay? But it seems dark matter just doesn't interact with anything at all, so we can't even detect it. That's the problem. So what we have here is the regular standard model that I just went over. And on the right-hand side is an extension of the regular standard model, and this is called the super-strength-inspired supersymmetric standard model. So the only theory that we have of quantum gravity is superstring theory at the moment. Well, we also have membranes, but it's another story. And it combines particle physics and gravity in 10 dimensions of space-time. So kind of hard to test. So what this is it's a low energy limit where the dimensions are folded down into 3-dimensional space-time. And so what you get is this symmetry. So just like we have symmetry between up and down quarks and this, we have a symmetry between quarks and squarks. So yeah, you put an S in front, so you get squarks, leptons, sup, down, stop, bottom. Gauge particles get interesting, gluino, neutrino, zeno, and Higgs zeno. Sounds almost Italian. So basically, it was on another slide, but the intrinsic spin of these quarks, these are actually all fermions that have a spin half. And the vector means that they're spin 1, so these vector have spin 1, spin a half, and this is spin 0, so that's a boson. So fermions are particles that have spin a half, and bosons are particles that have spin 0. So the symmetry here is actually to do with the spin. This has spin a half, and this has spin 0. This is a supersymmetric partner of the up quark. So this theory has gravity naturally built in. Now, what's interesting is that you can superimpose these particles, just like Schrodinger's cat there, that was the other Easter egg. You can superimpose these particles and you get something referred to as a neutralino. And this is a potential dark matter candidate from supersymmetry. Now, right now in the super collider experiments, there are, in fact, I've done a calculation, one of these calculations for a signature for such an event at a super collider. And if they observe this, then this is an indication of supersymmetry and possibly an indication of a dark matter candidate. But right now it's science fiction because we haven't found anything. So, so WIMPs are basically non-baryonic candidates. So there's axions, sterile neutrinos, weakly attracting. Gravitational interacting massive gifts and supersymmetric particles. So this is a candidate. Yeah, they come up with all these silly names. So as far as dark matter goes, it's a real zoo. Okay, this is a what do you call this? A mind chart. Of all the different theories. So you have dark matter, and you're saying on a weak scale, is it supersymmetry or little Higgs or so forth? Is it modified gravity and so forth? Is the matter hot, cold dark matter, warm dark matter, hot dark matter? What does that mean? Well, basically, cold dark matter means low energetic particles, warm means more energetic, and then means a highly energetic. The preferred model of the universe, using Einstein's model, cosmological constant, assumes cold dark matter as a candidate that adds into the theory. You may have heard of the cosmological constant. It's a kind of an interesting thing to allow you to at least add particle physics into the mix by looking at it in terms of the contributions to the energy in the universal energy density. So I just decided to do my own picks. Since I worked on supersymmetry, well, my first favorite is neutralinos, mainly because it also includes gravity. Axions are another one, which I would surmise they actually probably do exist, mainly because it's related to the symmetry of quantum chromodynamics. Whether or not it's a dark matter candidate is another question, but so far the standard model has all those particles you see, they're being predicted and found one after another. And it's based on symmetries, and this is based on the symmetry, so I think it's likely we will find those, but they're doing experiments on that. And then sterile neutrinos is an offshoot from the standard model, but basically neutrinos that don't interact with anything at all. So that's the whole zoo. Only found that interesting. So let's move along then. So here's an application. Here's a potential possibility of a dark star. So we talked about dark matter, black holes, and now we're on to dark stars. So in the early universe, apparently there are these supermassive black holes that are too big to explain normally. So they're thinking that in the early universe there was lots of dark matter and mixed with ordinary matter, and that through a process known as direct collapse, they form these black holes. Or through another process, they form these supermassive stars that are just bulging huge stars mixed with dark matter and normal matter, and they just sort of burn. They're not like normal stars at all. And this is sort of a reaction here that produces all these byproducts. So I like putting this up. It's just interesting to dream about, but it's probably highly unlikely. But with this type of stuff, you really should keep an open mind. Okay. So moving on then, let's look at the Big Bang Theory. So this is an inflationary model of the universe, and I happen to bring my own universe with me. So Unfortunately, I don't, well, you can't even really see it anyway, so I'll just let you use your imagination. But I have a balloon here, and I've drawn little galaxies and stars on it. And you could do this experiment at home. And basically, the surface of the balloon represents three-dimensional space. Okay? And so it represents how space is expanding. So we live on the surface of the balloon. And if you notice, when I blow on the balloon, you see there's a galaxy here, and they seem to be moving away from each other. And in fact, if you look, if I'm here, and I look here and here, everything's moving away from me. And as the bubble expands, it stretches bigger and bigger. And it turns out things farther away are even moving faster. Okay? And so we can actually have an expansion rate which tells us how much, like the rate at which the balloon is expanding, and you multiply it by the separation distance, and it tells you how fast something's moving away. So, for instance, the person way at the back there, if they're moving away from me at 60 kilometers an hour, the person in the middle, between me, is moving away at 30 kilometers an hour. So that's how the rule works. So we define something called the Hubble constant. And right now, the expansion rate of the universe, as we see it, is 70 kilometers per second per megaparsec. Okay? Now, a megaparsec is roughly the distance between here and Andromeda galaxy. So that's the length scale. So you have the rate of expansion per length scale. So if you multiply by 2, that gives you 2 megaparsecs. Something 2 megaparsecs away is traveling at 140 kilometers per second. So it's just a meter stick. So that tells you something about the expansion of the universe. And it also kind of tells you why I don't fly apart. Well, there's forces holding me together, but also the distance is very small. So, what else? Now, some interesting things. One thing to note is that at some point in the history of the universe, so it's called a Big Bang, but it's actually inflation. It's just space starts expanding. And in fact, as you know, nothing can travel faster than the speed of light, but space can expand faster than the speed of light. So that's just a workaround, I guess. So you could imagine that the universe expands, and at some point, particles are created, and you get this hot ball of gas. And one person gave it to me as an analogy: you take the sun and turn it inside out, and that's what you're looking at. It's this hot ball of gas. And as you expand more and more and more, the distance between the photons and stuff interacting between the ions and like charged particles gets further and further, and the photons get stretched into the red. And what you get is, left over, you get these stretched photons here, and this is the cosmic microwave background. Okay, so it's from the early universe. And it's interesting how that was discovered by accident. I think it was Bell. They had their horn antennas. This was 1940s, I think. And they were trying to do telecommunications, but there was all this noise in their antennas. And there's pictures of them scraping out pigeon poop and so forth. And after years and years of research, they found out that this noise was actually due to the leftover heat from the Big Bang, the actual background radiation, which corresponds to about 2.7 degrees Kelvin. So space isn't completely cold, but it's like minus 270 Celsius. So, okay, so let's look at this just a bit more. So the universe. So what's the fate of the universe? So it could expand, we put some energy, and then all of a sudden deflate, or it could keep growing and growing and growing, or it could grow and slow down. So the question is then, how do we measure the expansion rate? Actually, before I do that, there's one more slide, and it's just showing you how to look back in time. So remember, well, the speed of light is 300,000 kilometers per second. So when you look back into the universe, when you look across that balloon, it's taking light that time to get to you, and also it's stretched. It takes so when we look further back, things are dimmer and dimmer. We need more and more powerful telescopes to see further back. So this is sort of a history of how far we can see back. The redshift is really just a representation of how much the light is stretched, but it also corresponds to how many years we're looking back. So 6 billion years, redshift 1, redshift 700–800 million years, and this is sort of the distances we've been able to look back into the universe through these different telescopes. So the Hubble Space Telescope, way back to 180 million years. And then there's this James Webb Telescope, which there's some controversy about whether it'll get launched or not, but hopefully it will. It should be able to look further back. So this is just sort of, so when you're looking out there, you're looking back in time and you're looking at how galaxies form back in time. So when you're studying active galactic nuclei, you're looking at populations of galaxies, and you can actually, by looking at the different galaxies, you can tell how they're evolving. Like you say, oh, this is in this state, or it looks like there's another one that's in a different state. So you can, that's how you see, because the time scale on these things is way beyond our lifespan. So we just look at things quantitatively that way. Okay, so how do we tell the universe's expansion? How do we measure that? So, as I mentioned, if something's moving away from you, you get, so I should give an analogy here, which is the Doppler effect. Okay, so if in terms of light, if something's moving away from me, it's shifted into the red. If it's coming towards me, it's shifted into the blue. Okay, so if I have a car and it's coming towards me, you may have heard this like, well, that's, so it's a high-pitched noise, and then as it goes by, it goes, so you get this increase in pitch because the waves are being compressed as it's moving towards you, and then this decrease because the waves are being expanded. So when you look out into the universe of these objects, we know how the sun works. We know what the spectrum is in those lines that you see in the prism. We've done in chemistry lab. And what happens is, if it's on an object that's moving away from you, all the lines will be shifted down into the red, like the whole spectrum will be shifted. And by that shift, you can tell how fast it's moving. Now, so, and also you can tell how far away it is. So if you have like a standard candle, like if I took a light bulb, and I know it's standard lumens or whatever, and I put it here, I know what to expect when I put it so many meters away. I know how the light is going to fall off. Because I understand how that light bulb works precisely. So we need a standard candle. And the most standard, precise candle is type 1a supernovas. Type 1a supernovas are actually quite interesting, but basically you have a dwarf star, which is basically the burnt-out husk of a star. I believe that's what our star is going to become in the end. And then you have another star rotating around it, and its matter is being sucked into the star. And I may get this wrong. It's either the mass or the radius. I believe it's the radius. When it gets enough matter that it reaches a certain critical radius, and it's a very precise radius. It's referred to as the Chandra radius. As soon as that reaches that radius, it will explode, and you'll get a supernova resonance. Now, the interesting thing about this is the spectrum is the same all the time. So we know exactly what the spectrum is. We have to do some calibration stuff, but we know exactly the same spectrum, and we know the exact characteristics of this thing. It's so precise. And because of that, we can actually measure how far away it is and how fast it's moving. Okay? So we search through these to answer that question of whether the universe will continue expanding or stop or shrink. Okay? And so, which answer did we get? None of the above. Turns out the universe is expanding rapidly. All of a sudden, it's almost like you took a stick of dynamite, you made an explosion, and the explosion didn't dissipate, it just started getting bigger and bigger and faster. And I probably filled you with enough particle physics and everything else in in terms of dark matter because it's been heavily investigated. This is relatively new. This is like discovered in the 1990s. And the short answer, we have no clue what is going on. I mean, I could get into vacuum energy and quintessence and so forth, but it's speculation. Good for science fiction, I guess, until we get a better handle on it. But personally, I think until we get a better idea of what dark matter is, or some idea of a better theory of quantum gravity, it's going to be very tough to figure this out. But that being said, they are doing measurements, they are postulating things and testing things, and this is where science is exciting. Science is exciting when you deal with the unknown, just like vast radioverse. People ask me what they are. I don't know what they are, but it's exciting. Okay, so that's why we build these telescopes. That's why we build these machines. We're trying to discover our universe. Okay, so that's the closing. This is actually the last slide. I didn't remove the hiding stuff from here, but this is a cracking. So we've talked about black holes, dark matter, dark stars, and dark energy. So as advertised, that's the complete dark universe. Well, besides dark current and dark other stuff. So I thought that was okay.
I think we have probably a couple minutes for some questions.
Yes.
What you were saying was, really interesting. It's very comprehensive, and some things kind of snagged, but in a kind of like in a science fiction sort of way. Like you're talking about the dark energy and the dark matter, and the proportionality of the numbers indicates that the dark energy is expanding faster than the dark matter, which seems to indicate that the dark energy could be a form of inflation, and it could be decaying. And inflation inflates faster than the than it decays. But when it decays, gravity is introduced, and a form of matter is created. So that could be your form of dark matter. So what you have, in effect, would be inflation, which is dark energy, which is perhaps a different type of inflation, or maybe a continuance of inflation from the previous source, which turns itself when it decays into dark matter, which is not necessarily the same as matter because it's not the same sort of inflation. And also your dark matter would have mass.
Do you have a question?
Because your inflation.
So we've only got a couple minutes, so we can certainly talk about this if
Do you
possible.
have a question, or?
Well, I'll just leave it there. Food for thought.
Okay, because I should mention that in the early universe, in fact, there was no dark energy, it was zero, and the dark matter was about 63%. So what's been happening is that, in fact, the universe has been expanding as expected, and then all of a sudden, as the dark energy grew, then you got the rapid expansion. And it's almost like, basically, when you expand space, you produce virtual particles. And this seems to provide like an extra pressure that prevents stuff from collapsing. This is the more and more it expands, the more and more it fills, and the more and more as this negative pressure pushes out. So that's kind of along the lines of speaking. And this is a theory called quintessence. Yes?
That was Derek.
I was going to say, when you talk about the expansion of the universe being faster than the speed of light in the early stages of the Big Bang, have they really fully accounted for in some of these models the fact that when they're looking back, doing these observations, would there be a transition period where all of a sudden the expansion of the universe, like I'm imagining this thing going bang, and then you're
it's really open. It's an open question, but from my own biases, basically, I probably would be reluctant to change the speed of light. Mainly because it's very fundamental to.
Well, I mean, because you're coming up with periodic matters somehow coming into its own at a certain part in the universe. So why can we assume the speed of light would be anything?
If you buy into superstrings, and you start off in 10-dimensional space-time and you freeze it out, you can get up to, I think it's over 10 million possible different universes. And maybe in those universes, the speed of light has changed. Also, the fundamental forces will be different. It's like ice. There's 256 different forms of ice, and we're one of those forms. So, and those forms are the laws of physics. So when you create the singularity, the laws of physics are being developed as it. So the strong electroweak forces and gravitational forces, they're all on equal footing at that point. And then as you freeze out, they crystallize and they diffuse into these forces, if that's the way you want to look at it. So it's quite complex, yes.
The fact that the fact that we're expanding, does that sort of imply that the universe has an edge? Like if we're expanding, does the balloon have an edge?
Does the balloon have an edge?
Your balloon does, but in
No,
reality,
it doesn't. If I can get rid of the part where I'm blowing on it.
Okay. but is that? I'm just wondering if we're showing we're expanding into something. Do we have an edge, and what are we expanding into?
Well, we're kind of getting into philosophy.
Okay.
But in my own personal opinion, I like to think of a multi-universe where you have a sponge and the holes in the sponge represent different universes, and some are connected and some aren't.
Okay.
And the sponge is in a higher dimension. So, like, you could embed 3 dimensions into 10 dimensions, and they can live separately. Like if you have a flat sheet of paper and another flat sheet of paper, they're not aware of each other.
Right.
Of course, there's something called dark currents, where all the stars seem to be drifting to one point because maybe there's another galaxy near us.
Okay.
But anyway.
Take one more. Get ready.
Okay, yeah. Einstein, in his general relativity, special relativity, said, of course, everything is about perception, where you are, and the relative location. He said speed of light was constant, but your perception of it was not constant. Expansion seems to indicate that the speed of light will be exceeded or is exceeded in expansion. But all parts of that balloon, that expanding universe, are basically, from another point of view, exceeding the speed of light.
I don't think I explained that properly. The space, I'm not sure how to explain that in like 30 seconds or so. But no, in all these models and everything I know, the speed of light is a constant. But space itself, the fabric of space, it can extend. So you have an expanding surface, and that doesn't affect the speed of light on that surface. So there's parts that are expanding so rapidly away that the light will never reach us because of that. So there's sort of a horizon beyond which we cannot see.
Okay, I think we're gonna call it. There's 10 or 5 after 10. But I'll say thanks again. Great. And if you would like to continue these fun discussions of cosmology, many of us will be heading to Boston Pizza down on 7th. So we're going to join us. And thanks again. That was the meeting.